In the vast darkness of space, astronomers have discovered a new class of stellar predators, white dwarf stars that devour their own planetary systems. These cosmic vampires are remnants of stars like our Sun that have evolved into dense, compact objects with an insatiable appetite for their planetary companions. Unlike typical white dwarfs, these stellar vampires possess unique characteristics: metal-rich atmospheres, crystalline formations, and visible debris disks. As planets and asteroids approach these stars, they're torn apart by intense gravitational forces, creating a death spiral of debris that slowly feeds the stellar surface. The atmospheres of these stars contain heavy elements from consumed planets, providing a unique window into the chemical composition of distant planetary systems. Under extreme temperatures and pressures, the consumed planetary material forms exotic crystal structures, creating a cosmic light show visible across thousands of light years. The consumption process occurs in distinct phases, from initial planetary disruption to final absorption into the star's atmosphere. Recent observations have detected signatures of water-rich worlds being consumed, suggesting these stars are devouring planets that may once have harbored life. These vampire stars represent a distinct class of white dwarfs, characterized by their active feeding process and unique spectral signatures. By studying these stellar vampires, we gain insight into the potential future of our own solar system, as our Sun will eventually become a white dwarf itself. Let's explore the fascinating process of how white dwarf stars consume entire planets, creating one of the most spectacular phenomena in our universe. As planets get too close to these stellar vampires, intense gravitational forces begin to tear them apart. The debris forms a distinctive spiral pattern as it circles the star. The accretion disk forms distinct layers based on material density. Heavier elements sink toward the center, while lighter materials form outer rings. At temperatures exceeding 50,000 degrees Celsius, the planetary material becomes superheated plasma, creating brilliant streams of light as it's pulled toward the star. The destruction process occurs in phases: initial fragmentation, disk formation, plasma conversion, and final absorption into the white dwarf's atmosphere. Different elements create unique spectral signatures as they burn. Iron glows red, while calcium produces brilliant blue-white emissions, creating cosmic light shows. Astronomers can identify what types of planets are being devoured by analyzing these spectral signatures, revealing the composition of distant worlds. In the outer regions of the destruction zone, rapid cooling can create exotic crystal formations as vaporized materials reform in the vacuum of space. As planetary materials are absorbed, they create distinct layers in the star's atmosphere, fundamentally changing its composition and appearance. These cosmic events are so energetic they can be observed from thousands of light years away, serving as beacons that help us understand planetary system evolution. Let's explore the fascinating composition of these stellar vampires and the otherworldly crystal formations they create. But first, if you're enjoying this journey, hit subscribe. These white dwarfs develop unique atmospheres enriched with metals from consumed planets. The intense gravity and heat create stunning metallic cloud formations in their outer layers. Spectroscopic analysis reveals traces of iron, silicon, and calcium, clear signatures of rocky planetary material. These elements should sink into the star's core, but remain visible. As planetary debris cools in space around these stars, it forms exotic crystal structures. The process occurs in near-perfect vacuum conditions, creating formations impossible on Earth. Different crystals form at specific temperatures and distances from the star. This creates distinct zones of crystallization, each with unique mineral compositions. Some crystal formations can grow to enormous sizes, unrestrained by gravity. These structures reflect and refract starlight, creating spectacular astronomical light shows. The atomic arrangement of these space crystals differs from their earthly counterparts due to the extreme conditions in which they form. Crystal growth occurs over thousands of years as material slowly accumulates and cools. The process is driven by the intense radiation and gravitational forces of the white dwarf. Space-formed crystals exhibit unique properties: perfect symmetry, massive size, and unusual molecular arrangements that we cannot replicate in laboratories on Earth. These crystalline graveyards of former planets provide crucial insights into the composition of distant worlds and the ultimate fate that may await our own solar system. Let's explore how these cosmic vampires reveal the presence of water-rich worlds in distant solar systems, and what this means for our search for habitable planets. When water-rich planets are consumed by white dwarfs, They leave distinct signatures in the star's atmosphere, primarily oxygen and hydrogen in specific ratios. These spectral signatures tell us about the water content of destroyed planets. The strength of these lines indicates some consumed planets were up to 26% water by mass. Many of these discovered water worlds contained significantly more water than Earth, suggesting they were similar to theoretical ocean planets. As these planets are destroyed, their water undergoes phase changes from ice to liquid to vapor, creating unique signatures that persist in the white dwarf's atmosphere. The presence of dissolved minerals in these water-rich bodies creates distinctive crystal formations as the material cools in space. White dwarfs could potentially host habitable planets, and studying consumed worlds helps us understand what types of planets might exist in these systems. Different combinations of elements tell us about planet composition. High levels of oxygen, silicon, and iron suggest rocky worlds with substantial oceans. Recent surveys suggest water-rich planets are common in other solar systems, with roughly 35% of studied white dwarfs showing evidence of consuming such worlds. Future observations will help us better understand these systems and may reveal evidence of current habitable planets orbiting white dwarfs. As we look to the future, our own sun will eventually become a white dwarf. Let's explore what these cosmic vampires tell us about our solar system's ultimate fate. In about 5 billion years, our sun will expand into a red giant, engulfing Mercury and Venus, while Earth's fate hangs in the balance. This timeline shows our sun's transformation from its current state through red giant phase to its final white dwarf form, spanning billions of years. Our sun's white dwarf remnant will likely consume the scattered remains of our asteroid belt, creating metal-rich signatures similar to what we observe in other systems. Surviving outer planets will experience altered orbits as the sun loses mass, potentially leading to chaotic interactions and further planetary destruction. The extreme conditions around our future white dwarf sun may create stunning crystal formations from the remnants of our solar system. By studying current white dwarf systems, we can predict various possible outcomes for our own solar system's final configuration. If Earth doesn't survive, its fragments may create a debris disk around our white dwarf sun, leaving chemical signatures of our planet's existence. Current data suggests that 25 to 50% of white dwarf systems retain some planetary material, giving us insight into our solar system's survival chances. Understanding these stellar vampires not only reveals our cosmic fate, but connects us to a greater cycle of planetary evolution throughout the universe.